Hello IB students, today we'll be solving Physics HL Paper 2 2024. We'll be looking at question number 4. If you're interested in the other questions, go check out the playlist. I have put all the solutions there. Let's get started. A solid block of glass is covered with water. The diagram shows the path of a monochromatic light ray entering the water from the glass block. So we have an incident ray going from glass and refracts as it goes into water. The angle of incidence is given to us, it's 55 degrees, and the refracted angle is 71 degrees. The speed of light in the glass is 2.0 into 10 to the 8 meters per second. Calculate the speed of light in the water. State the answer to an appropriate a number of significant figures. Okay, so since we are looking at refraction, it makes sense to use Snell's law. You will find this equation in your data booklet. The equation for Snell's law is n1 over n2 equals sine theta 2 over sine theta 1 equals v2 over v1. Where n1 is the refractive index of glass and n2 is the refractive index of water, sine theta 2 is the sine of the refracted angle. So that's sine 71 and sine theta 1 is sine 55 equals v2 over v1. v2 is the speed of light in water and v1 is the speed of light in glass. Okay, this portion of the equation is what we need. Alright, so let's get rid of the refractive indices and let's use this section of Snell's law. Okay, so since we are looking for the speed of light in water, that's what we want. That means we are looking for v2. So we can rearrange this equation here for v2 as v2 equals v1 sine theta 2 over sine theta 1. Now we just have to plug in the values. So if I plug in the values, I have v2 equals 2.0 times 10 to the 8 sine of 71 degrees divided by sine of 55. Let's plug this into our calculator and see what we get. The calculator gives us a value of v2 equals 2.30 times 10 to the 8. Now since we want the appropriate number of significant figures, we must note that the input data has only two significant figures, 2.0. Both of them are significant. So we need to reduce this to just two significant figures. That would be simply 2.3 times 10 to the 8. That's our final answer. The speed of light in the second medium is 2.3 into 10 to the 8 meters per second. Alright, so we found the speed in water. Alright, let's have a look at the second part of the question. Explain the change in the wavelength of the light at the glass-water boundary. So what happens is, as light goes from glass to water, its speed changes. To be precise, its speed increases. Its speed increases from 2.0 to 2.3 right here. And what happens to the wavelength? Well, we can use the wave equation, which is v equals lambda f, and we can figure out lambda, the wavelength, from this equation. V over f. Since the speed has increased and the frequency always stays the same. When a wave goes from one medium to the other medium, the frequency never changes. It's just the wavelength that changes. And in our case, since v increases, that means lambda has to increase. So the change in the wavelength of the light is that it increases, and we can supply this equation as a reasoning. And that completes the second part of the problem. Let's move forward to the third section. The light ray is partly reflected from the glass water boundary. Draw on the diagram the path of the reflected ray. Okay, so what happens is we have some portion of the ray bends back into the medium. That is, it reflects. If it reflects, the angle of incidence has to equal the angle of reflection. So this is 55 degrees and this is the refracted ray. The next part of the problem says identify the direction of polarization of the reflected ray. Going back to the image here, so if we have a reflected ray that goes back into the glass, this angle is 55. The question wants us to figure out the direction of polarization. Well, if we look at the incident ray, it's both S polarized. These dots represent S polarization, meaning electric field vectors going into and out of the screen. It's also P polarized. P polarization, these electric field vectors are perpendicular. And we know from theory that whenever a beam of light reflects or refracts, the refracted ray, this one, it's going to contain both the P polarized and S polarization. So it contains both the dots and these perpendicular electric fields. On the other hand, the reflected ray, it's predominantly just S polarization. That means electric field vectors that point into and out of the screen. In fact, if this angle becomes 90 degrees, also known as Brewster's angle, then the reflected ray is perfectly polarized, is S polarized. It's just these electric field vectors that go in and out. But nevertheless, in all cases, the reflected ray is predominantly S polarized. Now this electric field vector that points into the screen is parallel to the interface. This interface here, the water glass interface, and the electric field lines, these are parallel. It's parallel to the interface. So we should say that the direction of polarization of the reflected ray is along the interface. And that completes this part of the problem. The water is removed and replaced with air. The refractive index of air is 1.0. The direction of the incident light is unchanged. Determine whether light emerges from the glass block into the air. So instead of having water, water is replaced with air. And they want us to figure out if the ray of light emerges. In other words, what happens is if this incident angle here, theta I, is greater than the critical angle, we get total internal reflection. In that case, the incident ray is not going to emerge from on the other side. At exactly the critical angle, if this incident angle is equal to the critical angle, what happens in that case? In the case of incident angle being equal to the critical angle, the refracted ray grazes along the surface. Let's figure out this critical angle. We can once again use Snell's law, which says sine theta 1 over sine theta 2 equals V1 over V2. Theta 2 is 90 degrees for the critical angle, so we have sine theta critical equals V1 over V2. How much is V1? V1 is the speed of light in glass, which is 2.0 into 10 to the 8, and V2 is the speed of light in air, which is a constant, which is 3.0 into 10 to the 8. From this equation, we can figure out theta c. That would be sine inverse 2 over 3. Let's plug this into a calculator and see what we have. This turns to be about 42 degrees. Since our incident angle is greater than the critical angle, we will have total internal reflection, meaning the incident ray is going to bend back into the same medium. There's not going to be any emergent ray, and that solves this part of the problem. So we figured out that no, the light is not going to emerge into the air. That's because the incident angle is greater than the critical angle, and the beam is just going to go back into the same medium. Alright, that completes this question. If you need more help, I tutor one-on-one and I'll be happy to help you. The link is in the comments below. Make sure to check out my previous videos and the next one. See you in the next one. Happy learning.